Welcome back, everybody. Today, I have the pleasure of showing you, I think, one of the most beautiful proofs in all of mathematics. It's the proof of Cauchy's theorem. Itself, a gigantic result, maybe the biggest result in all of elementary complex analysis. So I'm really looking forward to going through this argument with you. I remember when I was a student and I saw this proof shown to me by Eli Stein at Princeton, I was so stunned by the argument that I started to spontaneously clap. And I remember both my classmates and Stein looked at me like I was some kind of crazy person. But I just think it's an absolutely gorgeous piece of mathematics, and I can't wait to go through it with you. So, all right, let's dive in. So as I say, it is really one of the biggest results in complex analysis. It was discovered by Gauss, actually, around 1811, but as was often the case with Gauss, he didn't prove it. He didn't publish it. He kept it, lying around in his desk drawer, I imagine. And years later, Cauchy discovered the result. And so we call it Cauchy's theorem. The proof I'm going to show you, though, is not Cauchy's proof. It's actually a better proof due to a mathematician named Goursat. It's really magnificent, and it's better than Cauchy's argument in that it has fewer assumptions built into it. In fact, it's really sort of perfectly minimal. You'll see exactly where the assumptions get used, and there's nothing extra. So I would contrast that with the proofs in our textbook in Saff and Snyder. So they don't show Goursat's proof. They show two other proofs, one by a deformation of contours argument and another by invoking Green's theorem from multivariable calculus. But I can't say I really like those proofs so much. They are illuminating in their own way, but they sort of require you to understand the proof, let's say, of Green's theorem, which in my experience, a lot of students don't understand that to begin with. So I really think it's worth doing everything from the ground up. And the proof that we'll do here is exactly that. By the way, I will be writing out things in real time with you. I'm just going through some preliminaries here to save some time. So, but the juicy stuff we will work out in the usual slow, real-time way. All right, but let me remind you, a key result that we had from the last lecture and that we're going to use in this argument is that there's a whole class of integrals that we can instantly say are zero. If we integrate a power, an integer power of z minus a, so a is just some point in the complex plane, and if we look at z minus a to some integer power n, and then integrate that around a closed curve, any closed curve, gamma, we'll get zero. And the two caveats, though, this is not the case for n equals -1. We showed that that was special, that when we integrate for the case n equals -1, we got 2 pi I. But we're not going to be dealing with that case today. Instead, we're just focusing on these other integers and not equal to -1. And if we have that, oh, by the way, just to remind you, the reason this was true is that these functions, z minus a to the n power, we could instantly read off an antiderivative. Just z minus a to the n plus 1 over n plus 1, just like you would think in ordinary calculus. And the existence of an antiderivative then gives us this result that when we integrate around a closed loop, we get 0. So that was last time. Now, an instant implication of this result is that if we just have positive integer powers, or non-negative, like if we have a polynomial, so z to the 0th power times a constant, so c0, c1, z to the first power, c2, z to the second power, etc. If we just have these positive integer powers of z and integrate that, we're getting a sum of many zeros, we still get 0. So the integral of a polynomial is instantly implied to be 0 around any closed curve. Any polynomial integrates to 0. And so that probably gives you a feeling that lots of things will integrate to 0, and that's actually the point. That's what Cauchy's theorem says, that if we integrate any analytic function, f, doesn't have to be a polynomial, could have infinitely many terms in its power series, like sine of z or cosine of z or e to the z. Any analytic function integrated around a closed curve gives 0. But we have to be careful. The right statement is the function f should be analytic on the closed curve gamma and everywhere inside the curve. That's what we need. If we have those conditions, f analytic on and inside gamma, that's enough to conclude that the integral of f will be 0 around the closed loop. And it sort of seems astonishing at first because it feels like we're not assuming very much, just analyticity, but nothing else. And yet we'll see that that's exactly enough to give us the conclusion we want. This analyticity assumption is really much more potent than we first realize. That's a theme throughout complex analysis, that this very innocent-looking assumption of the existence of a derivative turns out to be a tremendous assumption with staggering implications. And so this is the first of those big implications, and we'll be seeing more of them as the semester goes on. All right, so that's what we want to try to prove. Let me say it a little more precisely. So here it is, Cauchy's theorem. Suppose f of z is analytic in a simply connected region R, and gamma is any closed curve in R, then the integral of f around gamma is 0. So here I should remind you about the topological concept of simple connectedness. As you probably have often heard it described, it means that there are no holes in the region. So I'm showing here some examples of, here's a region R, this blue region, doesn't have any holes in it, that's simply connected. Here's a region R, which does have a hole, this white region inside, that's a hole in the blue. And this is not a simply connected region, nor is this one, which has 2 holes. So the trouble is that in topology, there are many different concepts of holes, and so we should be a little more precise than this. So slightly more precisely, a region is simply connected if it has this property, that every closed loop in that region can be contracted continuously down to a point, can be deformed to a point, while staying within the region throughout the contraction. So for example, if I drew this closed loop, I could shrink it down continuously and stay within the blue region and contract it down to a point. But you see, that wouldn't be possible in this region, because if I happen to do a loop that encloses the hole, then when I try to shrink it down, I can only go so far before I get snagged on the hole. I can't shrink it all the way down to a point while remaining in the blue region. Of course, some closed curves can be shrunk to a point, like this one can. That's no problem. But there are some that cannot, the ones that enclose the holes. And so if you have a region like that, it's not simply connected. We'll see after I give the proof of Cauchy's theorem where we use this assumption. But for now, let me just go plowing into the argument. All right, so here it is. At this point, we can start writing. So the proof of Cauchy's theorem, I'm going to prove it first for a very special closed curve for a triangle. And then we'll build up more complicated curves out of triangles. But for now, let's focus on the case of a triangle. All right, so let's draw our triangle. Doesn't have to be equilateral, just any triangle. All right, so this is our closed curve gamma. And let's do it for gamma. Is a triangle. Actually, to emphasize that it's a triangle, I'm going to call it T. So there's my closed curve T. It's, as I say, it's going to be easy to generalize to curves beyond triangles. But for now, let's suppose that the triangle T has some diameter that we're going to call D. And a perimeter I'll call L. So these are some parameters that quantify the size of the triangle. When I say diameter D, what I mean is that if I pick 2 points in the triangle, look at how far apart they are. The distance Z minus W, that's always going to be less than or equal to D. For all Z and W, on the triangle T. So T refers to the boundary of this triangular region. And if we have this property that Z minus W can be no larger in magnitude than D for points on the triangle, that's also going to be true for all points within the triangle. Anyway, so that's how far apart points can get. And L, the perimeter, I just mean the sum of the lengths of the triangle. Now, it seems like at this point, to prove Cauchy's theorem, that the integral of f around this triangle is 0. How are you going to do that? We don't know anything about f other than that it's analytic. That's really all we have to go on. So this is the mystifying thing at this point, that somehow we have to use the fact that f of z is analytic to get the result we want. So watch this argument. It's amazing. The first move is stunning. Let's see. Maybe I should copy this triangle. Let's do that. I'll lasso it here. And let's duplicate that, drag it down here. Okay, so what am I going to do with that? Well, let's bisect the sides of the triangle first. So I'm going to break this proof into many steps. Here's step 1. Bisect the sides to make 4 new triangles. By doing the following. Take a point, here it is, bisect this side. Let me get rid of this little arrow that's in my way. And let's say I bisect this side. And then connect the dots. Try that again. And you see I've made 4 triangles. Now on the original triangle, the orientation was like this. Going around counterclockwise, as usual. So what I'm going to do is on the inner triangles, I'm going to respect that orientation, always go counterclockwise. So on this little triangle, we'll go this way on this edge. Let's try that again. It's insisting on drawing horizontal edges. Let's try that. Okay, like so. And here, we'll go this way. And here, like so. But that innermost triangle also requires to be its edges to be traversed counterclockwise, or at least that's going to be convenient to do. And so let me put in, I'm now referring to how I am going to integrate around the inner triangle, going this way. And you'll notice that those inner edges are getting counted twice, once in each direction. That's going to be a key point. In fact, it lets us observe that, that the integral of f of z dz around t, which is what we're interested in, that's just exactly equal to the integral of f of z dz around the four little triangles. And here's why. I mean, if I take the sum of the integrals over all those little triangles, like say this one, got a contribution from this edge, and this edge. But now if I add the integral around that triangle to the integral around this triangle, the key thing to notice is that this edge is being traversed twice, once in each direction, once this way and once this way. And so those contributions from that edge will cancel out. We pointed this out last time, that when you go along an edge in one direction, you get the negative of the integral if you go the other direction, because all the dz's change sign. So all those internal edges are going to cancel out. Or maybe say it a little more precisely, the contributions to the integrals from the common internal edges cancel. Okay, so that's step one. Now, in step two, we're going to look at the triangle, the small triangle, that has the biggest integral in absolute value. And you'll see why. We're going to build up an inequality that's going to give us the result we want. So in step two, let us choose the little triangle with the largest integral in absolute value, in magnitude. And I'm going to call that triangle T1. If there's a tie, if two triangles happen to have the same magnitude of the integral, and that's the largest, pick one of them arbitrarily, doesn't matter which one. So, but the point being, having chosen the one with the biggest integral, then by the triangle inequality, no pun intended, I can bound the magnitude of my original integral by saying it's less than or equal to 4 times the magnitude of the integral over the little triangle that gives the biggest contribution. Right? Because by definition, that triangle T1 gave me the biggest absolute integral. And so if I use that 4 times, I guess what I'm saying is I should think of this integral as the sum of 4 integrals, meaning each of these over the 4 little ones in this picture, and then putting absolute value around all that and applying the triangle inequality I get. And then picking the definition, using the definition that T1 gives the biggest integral, I get this. All right, hope that makes sense. And now maybe you can start to see the strategy. Like a maniac, we are going to keep playing this same game again. We're going to keep bisecting all the triangles to make littler and littler triangles. It'll almost remind you of a fractal. So in step 3, we are going to play the same game. Play the same game again, but now with triangle T1. So in other words, if I take this picture and copy it, well, actually, yeah, all right, let's do that. So duplicate, come on down. So what am I going to do? Like, let's suppose that this triangle in here, I'll make it heavy, was the T1 of that. This one turns out to be the largest. So what I'm going to do at the next stage is again bisect the sides. And pick out the triangle of those 4 that gives me the biggest integral, and do the same argument that I just did. And I'm going to keep doing that. And at the nth stage, I'm going to call the triangle that I've focused on T sub n. My pen got a little bigger. Maybe I mean this one. So at stage n, call the triangle Tn. So that is the triangle with the largest absolute integral. Of f around it. Call that one T sub n. So what we're going to get, repeating the argument, I mean, if you just look back at what we did, here we got a factor of 4 by doing one stage of the argument. If we repeat the argument n times, we're going to get a factor of 4 to the n. So repeating this strategy, we get, excuse me, integral of the original f of z around the original triangle T. It's going to be less than or equal to 4 to the n absolute value integral around Tn f of z dz. Okay. Sorry, you need absolute value on this too. All right, so we have this inequality. Now, what's the strategy of this proof? We're going to try to show that this left-hand side is bounded above by this quantity, and we're going to show that that quantity can be made arbitrarily small. Which sort of seems amazing, considering that at the moment it's building up like 4 to the n. It looks like it's getting monstrously large, and yet it's going to turn out that we can take this whole thing and make it smaller than any desired positive number. And that will allow us to conclude that this side is actually 0. So how does that work? Well, think about what's happening in this picture. You know, this one, where I'm doing my little fractally construction. Try to think about what would happen at the next few stages. Like, let's do a few here. So, whoops. The dangers of this new technology. So here's a triangle. I bisect, get something else, bisect again, pick some other triangle in here. Like, let's suppose we're always picking the central triangle. Maybe those happen to be the biggest, just so I can draw something convenient. You see what's happening. It looks like I'm zooming in on something very tiny. And the argument is that as I keep doing this sequence of triangles, always picking the one with the biggest integral inside the previous stage, do you see we've got this shrinking family of triangles, and it looks like it's sort of converging on a point? That's actually correct. That we can say, and this is now step 4 in the argument, that there's actually a point. In fact, a unique point. I'm going to call it A. That is caught or trapped in the infinite nested intersection meaning, all these common interiors of, like, so it's the intersection, say, of the region inside this triangle, intersect with the region inside this triangle, which really is just then that triangle's region itself, intersect with this region, intersect with that, and so on. In the infinite nested intersection of all those triangles, there is a point in there. It's not converging on a hole. There's actually a point in there. That may seem intuitively obvious, that there is a point, as opposed to some kind of emptiness, but that requires proof, and also that the point is inside the original triangle, didn't somehow magically get outside. It does seem obvious, but it's the kind of thing that does need proof. I'm not going to show the proof of that step. That's something that you would learn in a course in topology or point set topology, or a good course in like advanced calculus or something. It uses compactness. So this step requires proof that I'm not going to give. It uses the fact that the triangle and its interior together, in other words, the closed triangular region, form a compact set. So the compactness is exactly what ensures the existence of this point A. So there's some, like in this diagram above, there's a point A sitting in there. A is in there. So I could write it this way, kind of abusing notation a little bit. Let me think of the region T, T not just as the boundary triangle, but as the whole region. I'm saying that this A is sitting inside as a subset of ... which is a subset of T2, which is a subset of T1, which is a subset of the original T. And so if you wanted to visualize it, imagine like at the nth stage where n is some large number, maybe you've done 10 or 100 iterations of this. What would you see if you could zoom in? I could like sort of blowing up this picture. What you would see is nothing that amazing. You would just see something that looks like a little triangle with a point A inside. And this is triangle TN. Okay, still not clear how, we haven't used analyticity yet. All we've done is this crazy triangle construction so far. But stand by, because we're building to a climax. So now, step 5. Can we estimate if you go back to this step right here, look at this key inequality. Maybe I'll put that in a box. I've got this inequality here in the blue box. I want to try to estimate how big can this integral be over that tiny triangle Tn. And is it going to be tiny enough to offset this growing exponential? All right, so this is what we want to estimate. How big is this integral over the tiny, tiny triangle Tn? All right, well, let's see. All right, well, of course, the answer is yes, we can, because Tn is so tiny. So what can we say about what's going on there on Tn? On Tn, we can approximate our function f of z. This is where we're going to use analyticity. We can write f of z equals, now not just approximately, that actual equality, f of z equals f at this point A inside the triangle plus f prime at A, excuse me, f prime at A times z minus A plus a term that I'm going to call epsilon of z times z minus A. And that's exact. In fact, think of this as a definition of this function epsilon, where, here's the cool thing, epsilon of z is a function that tends to 0 as z approaches A. Which is why I'm calling it epsilon. You should think of it as very small. But actually it tends to 0 as z goes to A. Now, all right, so let's unpack this. I mean, because this is the key step right here. Excuse me, I want to add some pages. Let's see here. Let me add a few pages. Okay. This is a key step right here, this line. Because this is exactly the statement that f is analytic. This is where we're using analyticity. Using the hypothesis that f of z is an analytic function. So let's see how. I mean, how exactly? I mean, it looks a little weird the way it's written out, but if you solve for epsilon of z the way I've defined it, it'll make more sense. Just solving for epsilon of z, here's what it is. It's f of z minus f of A all over z minus A minus f prime of A. And of course, the expression here, this difference quotient, we know converges to f prime of A as z approaches A. We know that that limit exists because f is assumed to be analytic. And it's also assumed to be analytic on the triangle and everywhere inside the triangle And so we know that f prime of A does exist, that this point A is inside the triangle and that f prime is defined there, and that this limit exists. And also that the limit of this expression equals the limit of this expression, equals this constant as z approaches A. I call this a constant because this doesn't have any z dependence. It's whatever that number f prime of A is. So the key thing here is that the smallness of epsilon, the statement that epsilon goes to 0 as z goes to A, is the statement that f is differentiable at the point A. And that's all. And we know that this differentiability holds because we've assumed f is analytic. So anyway, the key point being that this expression, this epsilon, is small for z close to A. Since f is analytic. All right, so we've now used the analyticity, and watch what happens. Now, remember, the reason I'm doing this is I want to calculate or estimate f of z dz around this tiny triangle Tn. And so let's integrate the three terms. Here they are. This is a constant. This is a constant number times the simple polynomial z minus A. And then there's this kind of uncontrolled thing, which is a z minus A times a small function epsilon. And even though I say it's uncontrolled, it's under enough control that we'll get what we want. So watch, we're going to integrate each term. Here we go. Integral of f of A dz plus, this is all over Tn, plus the integral over Tn of f prime of A z minus A dz, and finally plus integral over Tn of epsilon z times z minus A dz. So that looks like a lot, but actually keep in mind that A is just some number and f of A is also just some complex number. These are constants. And so this comes outside, if you like, the integral. And so really what we're doing is just integrating dz around a closed loop. And here's where I want to remind you of this fact that I mentioned at the very beginning of the lecture. Let me go back here. This one. That if I integrate a integer power of z, or z minus a constant, z minus A, any integer power of A around a closed loop gives 0 by that antiderivative argument, because this has an antiderivative. Again, not worrying about this case, which isn't going to come up here. We get 0 for such integrals. And so our first two integrals below, in the stage that we're at right here, this is going to integrate to 0 by the argument that I just made. And similarly, when I integrate this function, z minus A, around a closed loop, it has an antiderivative of z minus A all squared over 2. Around a closed loop, that integrates to 0. So that term is gone as well. And that's looking pretty nice because now, right, so as I say, these are special cases of integral of z minus A to the n around a closed curve is 0. So I'm just left with that third integral to deal with. So these were the n equals 0 and n equals 1 case. All right, so what do we have? We have, as our conclusion at this stage, the integral around this tiny triangle of f of z dz is the integral of epsilon of z, z minus a, dz. I'm sorry, the original one was not around Tn. This is just around the big triangle, T. No, I'm sorry, I do mean Tn. I do mean Tn. My bad. Okay, yeah, right. And that was the point, that we're trying to estimate this integral around the tiny triangle. So let's look at its magnitude. It's exactly the magnitude of this. And now what to do? Well, we don't know much about epsilon except that it's small, but that's enough to give us what we want, because in the last lecture, I introduced this inequality that's crude but effective that we called the ML bound. And so now's the time to wheel out the ML bound. That's step 6. So the ML bound would tell us that, so we're trying to estimate how big can this be. It tells us that integral over Tn epsilon z, z minus a, dz in magnitude is less than or equal to, so what do I need to do? The ML bound says you got to take the max of the integrand in absolute value, that's your m, times the length of the contour of integration, that's your L. All right, so what is the max? Let's just write it all down here. I would take the max for all z on the contour of integration, Tn, of epsilon of z. And I also want to take the max of this part of the integrand, z minus a. That's where the diameter comes in. What's the max of z minus a for all z's on the boundary, on the triangle? Well, a is somewhere on the interior, or even if it were on the triangle itself, z minus a in magnitude can't be bigger than the diameter of that little triangle. So we can just put in a bound here of diameter of Tn. That now takes care of this term. And then finally, we have to talk about the length of Tn. So that comes in as well. That's our L. Okay, so diameter of Tm and then times the length of Tn. Okay, and well, what have we done to construct Tn? We just bisected the sides of earlier triangles. So in fact, if you look at the construction, the diameter is going to be going down by a factor of 2 with every bisection, and so is the length of the triangle. That is, we have here the max z element of Tn of epsilon of z. This diameter can be compared to the diameter of the original triangle by having gone down by a factor of 2 to the n with each after n iterates. And the length has also gone down by that same factor, 2 to the n. Since Tn was constructed by repeated bisection of T. Okay, and now we're almost done. Step 7 is to put everything together and watch how amazingly this all cancels out. Take the integral of f around our original triangle. Look at its magnitude. We have argued that this is less than 4 to the n times the magnitude of the integral over triangle Tn, defined as the one with the biggest integral at its stage of bisection. And by what we've just argued, I mean, there was this fantastic cancellation here. This, I mean, as you look back at what makes this proof work, it's the exact zeroness of these two terms due to the antiderivative condition and the fact that we can represent f in this way by analyticity. We get exactly the cancellation we need, leaving us only with this little term. And watch. Here we have 4 to the n magnitude epsilon z minus a, integral over Tn dz, which we just argued was, here we've estimated this integral above right here. So let me copy all of this expression. Actually, maybe I'll literally copy it. Let's do that. You can see I like using my iPad. Let's say duplicate, come on down here. And look at that 4 to the n canceling with those two factors of 2 to the n. Isn't that nice? So zap, zap, and zap. And so we have two constants, d and l, and then the max of epsilon z. And now the final stage in the argument is just think about what happens as n gets large. So as n goes to infinity, we know that the maximum value of epsilon of z goes to 0. Because that's what we said, this function epsilon goes to 0 as z approaches a, and as the triangles shrink, all the points on those tiny triangles are approaching a. So we can make this max as small as we want. That is, if you fix some tiny number, if you call it delta or whatever you want, you can, by picking n large enough, you can make this max less than any pre-assigned positive number delta by the analyticity, as we argued earlier. So we can make the right-hand side of this inequality right here. We can make this right-hand side arbitrarily small by making n as large as needed. But the key thing is that this left-hand side does not depend on n. It doesn't know anything about our bisection procedure. It's just some number. It's a non-negative number. It's a magnitude. But whatever this non-negative number is, it's less than any prescribed positive quantity. So it has to be 0. And that's it. The left-hand side is independent of n. So it must be equal to 0, which is what we're trying to prove. And that, ladies and gentlemen, is Goursat's proof of Cauchy's theorem, at least for the case of a triangle. All right, so let's take a little breath. Very good. And I guess I want to just make one little remark before I sign off. which is where did we use the simple connectedness? Like why was that important? That looks like n factorial. I see up here, I think I'm going to delete that. Where did we use the simple connectedness, just to make sure that that's clear to you? Let's see, I can delete this page. And this one. Yeah, so I pre-wrote out a few little comments about that. Where did that come in? But the reason we need the simple connectedness assumption, remember we said F was defined to be analytic throughout a simply connected region. If we didn't have that simple connectedness assumption, we could get into trouble because we could have an example like this. Look at this blue region R. That region R is not simply connected. It has a massive hole in it right here. And it happens that the origin is sitting inside that hole. The origin is not in the blue region, but it is in the hole. Now, if we integrated the function 1 over z, we integrated 1 over z around a closed curve gamma that encircles the origin. We showed in the last lecture that that gives us 2 pi I. And that would look like a contradiction, maybe you might think, to Cauchy's theorem, because after all, I mean, our function f of z equals 1 over z, perfectly analytic in the blue region, no problem there. Yet, the integral of f around gamma is not 0. So what's going wrong? And the problem is, I mean, how is this possible? It's because this function f of z equals 1 of z, although it's analytic in the blue region, it is not analytic everywhere inside gamma. That's the problem. Remember I said you want f to be analytic on and inside gamma. That is not the case here because f is not analytic at this point 0 that lies inside gamma. So that's the trouble. When you have a non-simply connected region, you can have points that cause difficulty that are not in the region, yet are inside the curve gamma. So our simple connectedness assumption in Cauchy's theorem, the hypotheses of Cauchy's theorem, excludes examples like this as we need to. Okay. So I think that's all I want to say about Cauchy's theorem. I hope you like that proof. Incidentally, maybe it's worth saying one little thing, which is that why are triangles enough? I mean, once we have the result for a triangle, then, I can build up more complicated shapes by adding more triangles. Whoops. So, like think of a curve that's sort of complicated and polygonal. I can prove Cauchy's theorem for a curve like that because I can build up this region inside out of triangles. And since I have Cauchy's theorem for triangles, and I have all these internal edges with that kind of cancellation argument that we made earlier, you can prove Cauchy's theorem for any polygonal curve by this kind of argument. And then finally, for any smooth curve that can be well approximated by a polygonal curve, Cauchy's theorem will follow there. So for a sufficiently nice curve that is approximable by polygonal curves, Cauchy's theorem will hold. All right, so I hope I haven't lost you in the details and that you were able to enjoy what a really magnificent proof that was. Okay, all right, thanks for watching.